warm welcome to all the viewers for the course Advanced Manufacturing Technology and myself Thiapal, Assistant Professor of Department of Mechanical Engineering, JS College of Engineering, and today I am going to give a brief lecture on electric discharge machining. Already in the first part of electric discharge machining, I have already elaborated the process that has been occurring while functioning, and I have also mentioned what are the process parameters that are evolved to perform the operation. So right now in the second lecture of electric discharge machining, we are going to consider all the process parameters, all the equipments that are associated with this particular machining. So without delaying, let's come to the point.
Well, today in this second lecture of EDM, today we are going to discuss the rest of the components, its application, advantages and disadvantages of EDM. So let's proceed. So right now we are going to talk about the flushing system. So why and what is the basic importance of a flushing system? Now we are going to have a look here right now. So as you can see that one of the most important factor for a successful EDM operation is the removal of the debris, or which is commonly known as the chip, from the work gap. But how is it performed? So first of all, you can see that flushing of this particle out of the working gap is very important to prevent the forming breaches which causes short circuit. And from here you can have a look right now that EDM have a built-in power additive control, and that increase the pulse spacing. As soon as this happen, it reduces or shut off the power supplies too. Next, flushing is basically a process of introducing clean filtered dielectric fluid into spark gap. In flushing is not applied correctly manner, then it can result in erratic cutting and poor machining conditions too. Flushing of dielectric plays a very important role in maintaining a stable machining and the achievement of close tolerance, and also it helps to get a high surface quality product. Well, inadequate flushing can also result in arching. It decreases the electrode life and also at the same time increase production of time too. Thus, from all this particular point, you are able to see how important it is for a flushing system. Now here we are going to discuss about the EDM flushing method. What are the method you can see? That is normal flow, reverse flow, jet flushing, another is immersion flushing. So in normal flow, what you can see is that basically this is the electrode and this is also an electrode, and you can see the dielectric inlet has been shown here by giving an arrow. In normal flow, what is happening, it is getting inside here and then it is getting out in this particular manner. So this is a normal flow. Now if I talk about the reverse flow, then you can see that right now the inlet is from different direction. In normal flow, the outlet became the inlet for the reverse flow. And you can see the flow of dielectric is occurring. It is passing through this particular gap. And next what is happening, it is getting out here. That is the dielectric outlet. Now, since we are discussing about the flushing system, as you can see, normal flow, that is the thing where you can see is that dielectric is introduced under the pressure. Though or you can say through one or more passage in the tool, and is basically forced to flow through the gap between the tool and work. The flushing holes are generally placed in areas where the cuts are deepest. And the most important thing is that normal flow is sometimes undesirable because it produces a tapered opening in the workpiece. But if I have a look for the reverse flow, then you can see that particularly useful in machining where the deep cavities dies is there, where the taper produced using the normal flow mode can be reduced here. The gap is submerged in filtered dielectric portion, and instead of pressure being applied at the source of a vacuum is basically used. With clean fluid flowing between the workpiece and the tool, there is no side sparking and therefore no taper is also produced. Now we will be talking about the jet flushing system. So here what is told is that in many intents, the desired machining can be achieved by using a spray or jet of fluid which is directly against the machining gap. So if there is any sort of machining gap, you can do what? You can spray the fluid over that particular section. And the most important thing is that machining time is also longer with jet flushing than with the normal and reverse flow method. Or you can say the machining time is also longer with jet flushing in respect to normal and reverse flow modes. Now we will be discussing about immersion flushing. For many solo cut or perforating of thin section, simple immersion of the discharge gap is really sufficient. Cooling and debris removal can be enhanced during the immersion of cutting by providing relative motion between the tool and your workpiece. And the most important thing is that vibration or cycle interruption compromise the periodic reciprocation of the tool relative to the workpiece to effect a pumping action of the dielectric. So if I make a glance of immersion flushing system, then it is basically preferred for solo cut or perforation of thin section, or you can say simple immersion of the discharge gap is sufficient. And of course, cooling and debris removal can be enhanced during immersion cutting by providing a relative motion between the tool and the workpiece. Now if I talk about the synchronized pulp flushing, it is also available in some machines. Now with the method of flushing occurs only during the non-machining time as the electrode is retracted slightly to enlarge the gap. So you have to keep it in mind that flushing method occurs during the non-machining time. The electrode is retracted slightly to enlarge the gap. And if you want to increase your electrode life, has been reported to in this particular system. Innovative techniques such as ultrasonic vibration, and if it is coupled with mechanical pulse EDM, then jet flushing with sweeping nozzle and electrode pulsing are also investigated by the researcher Masuzawa in the year 1990. So these are the upgradation or the development that has been took place already with EDM process. Now if I ask or if I discuss the 4 proper flushing conditions, and it has been recommended in the year 1989 in a metal handbook, that is, flushing through the tool is more preferred than slide or side flushing. As you can know, the Metal Handbook has recommended us few of the points regarding the flushing system, and one of the most important is that it is always preferred than side flushing. Next, many small flushing holes are better than few larger ones. So small holes are basically preferred, or it is much better than your larger one. Third is that the steady dielectric flow on the entire workpiece electrode interface is desirable. So a steady dielectric flow must be there within the entire workpiece and the electrode interface too. And the spot that has been created by pressure flushing from opposite side of the workpiece, that should be also avoided. Eventually, if I talk about the vent hole, that should be provided for any upward concave part of the tool electrode to prevent the accumulation of explosive gases. And of course, a flash box is also useful if there is a hole in the cavity. So what I was talking, that these are the proper flushing condition that has to be recommended or that has to be followed while machining. One of the important is that the flash box, which is very useful, that should be there in a hole in the cavity. Now we will be discussing about the process parameter. As you have already seen there, that so many parameters we have already talked in the first lecture of EDM. That is, the wave is characterized. I have shown you the wave formation. But basically, what are the factors that is helping it to get formalized? So that is none other than open circuit voltage, that is always denoted by V0. The working voltage, that is the VW. Next is your maximum current, that is the peak current. It has been denoted by I0. The pulse on time, that is the duration for the voltage pulse is applied, that is always recommended as T on. The pulse of time, that is denoted by T off. The gap voltage between the workpiece and the tool. And the most important thing is that the spark gap that has been formed as delta. The polarity, which is, it can be straight polarity, that is the tool is negative, and the dielectric medium, and as usual external flushing through the spark also. As you can see, this is the process parameter, that is the VW voltage, this is the current, and you can see the T on. This is the pulse on time, this is the pulse of time. You can see the wave form getting straight. Then there is a pulse of time, again it is getting this one. So this is the thing, and you can see this is the peak current, and this is basically varying with respect to your time. Voltage varying and current varying with respect to time. Now we will be talking about EDM type, and one of the most important, or one of the type of EDM type we are talking about right now, that is the sinker EDM. And sinker EDM is also called cavity type EDM, or it is also known as volume EDM. Well, constant of an electrode and the workpiece submerged is an insulating liquid such as oil or other dielectric fluid. And the most important thing is that the electrode and the workpiece are connected to a suitable power supply. And basically the power supply generates an electric potential between the two parts. As the electrode approaches the workpiece, the dielectric breakdowns occur in the fluid, forming a plasma channel, and the small spark jumps. And this spark basically happens in huge number at seeming random location. Now as the base metal is eroded, the spark gap subsequently increases. And the most important thing is that the electrode is lowered automatically so that the process can continue. Next important thing is that several hundred and thousands of sparks have been occurred already in per second, with the actual duty cycle carefully controlled by a step setup parameter. And basically this controlling cycle are sometimes known as on time and off time. Basically pulse on time and pulse off time. Now as you can see that one time setting, or you can say the on time setting, determines the length or duration of the spark. So as we were talking that EDM, and that is also a type of sinker EDM, the most important thing is that you can see that the power supply generator basically generates an electrical potential difference between the two parts. And this spark basically happens in huge number at seem random location. And the base metal is electrode, and the spark gap is subsequently increased, and the electrode is lowered automatically so that the process can continue. And this is basically control cycle as pulse on time and pulse off time. Now the time on time setting determines the length of the duration of the spark. Hence, a longer on period, a deeper cavity basically occur. And this helps to create a rough finish on the work surface. The reverse is also true for shorter on time. That is, if the time is shorter, the surface roughness is much better. Off time is a period of time that on spark is replaced by another. A longer off time, for example, allows the flushing of dielectric fluid through a nozzle to clean out the eroded debris, thereby by avoiding a short circuit. And this setting can be maintained in microseconds. And this is oftenly used to get a part or to get a geometrical part of complex 3D shape, and often with a small or odd shape angles too. So if I talk about the EDM, then the next part is your wear EDM. It is commonly known as wear cut EDM, and also it is known as wear cutting, where you can see a thin single strand metal wear. Basically we prefer brass, which is feed through the workpiece and submerged in a tank of dielectric fluid, which is typically deionized water. And basically you can cut the plate of thickness around 300 millimeter. You can also make a punch, tool and die for hard metal that are very difficult, that is to be machined with other methods or any conventional methods. Uses water as its dielectric fluid. Its resistivity and the other electrical properties are also controlled with the filters and deionizer unit. And the water flushing the cut debris away from the cutting zone. Flushing is a very important factor to determine the maximum feed rate for a given material thickness. And commonly it is used when low residual stresses are desired, because it does not require high cutting force for material removal. Now we will be talking about the material removal rate, which is commonly known as MRR. And here you can see that material removal rate or if you talk about the surface quality or accuracy, all are basically interrelated with the pulse characteristic. So crater volume, that is the actual existence through which you're going to determine the surface quality. So it is basically depending upon your pulse rate, as well as pulse rate is directly associated with the material removal rate, surface quality and accuracy. While crater volume is also associated with the dielectric properties. And this crater volume is created with the help of this tool electrode and the workpiece thermal property too. And tool electrode is associated with material, movement and wear, as well as the workpiece thermal property that are considering melting point, boiling point and conductivity. So these are all the parameters that are affecting the EDM performance. So you have to keep in mind that ultimate result is your material removal rate, surface quality and accuracy. But the parameters that are controlling the entire thing, it is all about the pulse characteristic, tool electrode, workpiece thermal property, of course dielectric fluid. Now we are talking about the EDM material removal rate, where you can see that EDM metal is removed from both the workpiece and the tool electrode. The MRR depends not only on the workpiece material but also on the material of the tool electrode. And the machining variables such as pulse condition, electrode, polarity and the machining medium all are interrelated. And in this regard, material of low melting point has a high metal removal rate and hence rougher surface finish. Well, typical removal rate range from 0.1 to 400 millimeter cube per minute. And if I talk about the MRR or volumetric removal rate, then it is 3 millimeter in basically the unit is millimeter cube per minute, which is described by Kalpak Jain in the year 1997. So MRR can be, or you can say VRR, volumetric removal rate. It is denoted by the formula 4 into 10 to the power 4 ITW, where I is the EDM current and TW is the melting point temperature of the workpiece. So this is a very important formula for getting MRR. So as you can see, this is the EDM material removal rate. Various spark is generated and the crater is occurring. This is the pulse current, how much current they are providing and what are the surface roughness it is achieved, it has been mentioned here. Now this is the effect of pulse on time, or that is called the energy on MRR and surface roughness. So you can see this is the surface roughness you are getting. This is the pulse current. This is the tool and this is the workpiece and this is the crater that has been generated. Now we are talking about the surface integrity. Means what is the surface integrity? Basically the surface condition that is going to be described. So surface basically consists of multitude of overlapping craters that are formed by the action of microsecond duration spark discharge, and the crater size depends on the physical and mechanical properties of the material, and you can say composition of the machining medium, discharge energy and duration. So integral effect of 1000 of discharge per second leads to the machining with a speed, specified accuracy and surface finish too. Now depth of crater, basically the peak to the value maximum of surface roughness, and maximum depth of damage layer can be taken as 2.5 times of that roughness. And according to Delpriki in the year 1977 and Motokoi and Lee in the year 1968, The maximum peak to valley height, that is always denoted by RL, was considered to be 10 times than RA, that is the surface roughness. And the average roughness can be expressed in terms of pulse current, that is the IP, and pulse duration, that is the TP, and the formula has been already imparted here. And surface roughness increased linearly with the increase in MRR. So we know if there is a lot of MRR is occurring, then the quality of the surface roughness will be not a good one. In the year 1978, Jeswani, who told that graphite electrode produced rougher surface than metal one. And in the year 1991, Konedia and Furuya claimed that the introduction of oxygen into discharge gap provides extra power by the reaction of oxygen. Thus, this is turned increased workpiece melting and created greater expulsive forces that increase MRR and surface roughness also. The choice of correct dielectric flow has a significant effect in reducing surface roughness by 50%, and also it is increasing the machine rate and lowering the thermal effect in the workpiece surface. Lastly, the dielectric have always a low viscosity, which are recommended for smooth surfaces. Now, if I talk about the surface integrity in respect to metallurgical change, then the temperature in which the changes occur is between 8000 to 12,000 degrees Celsius. An additional thin recast layer also occur of 1 micrometer to 25 micrometer, that depends on the power used. How much power it has been used, that depends upon that. Next is that Dilpreet in the year 1977 and the Levy and Maggie 1990 claimed that the heat affected zone basically adjacent to the solidified layer which reaches 25 micrometer. Some annealing can be expected in the zone just below the machine surface. Now, not all the workpiece melted by discharge is expelled into dielectric. Remaining melted metal is quickly chilled primarily by heat conduction into the bulk of workpiece, which resulting in an exceeding hard surface. Now, depth of anneal layer is proportional to power used. And the most thing is that it ranges from 15 micrometer to finish to 200 micrometer for higher MRR. And one more thing is that annealing is usually about 2 points of hardening below the parent metal for finish cutting. Now, in rough cut, the annealing affect 5 points of the hardness below the parent metal. An electrode that produces more stable machining can reduce the annealing effect. A finish cut can be removed by the annealing material by the previous rough cut, and the altered surface layer significantly lowers the fatigue strength of alloys. It consists of a recast layer with or without microcracks. Some of these may extend into the base metal. Pulse metallurgical alterations such as hardening and tempered layer, heat affected zone and intergranular precipitates, and during EDM roughing, the layers showing microstructural changes including a melted and resolidified layer is less than 0.127 mm deep. During EDM finishing, it is less than 0.075 mm, and post-treatment to restore the fatigue strength is recommended to follow EDM of a critical or highly stressed surface too. Now, in the surface integrity, there are several effective processes that accomplish the restoration or even enhancement of the fatigue property. And this method basically recruits is a removal of altered layer by low stretching grinding or chemical machining, addition of a metallurgical type coating, reheating, and application of sort painting. Now, what are the EDM characteristics? Let us discuss in a brief. First of all, it can be used to machine any work material if it is electrically conductive. Next is material depends on thermal property rather than its strength, hardness, etc. Next point is the volume of the material removed per spark discharge is typically in the range of 1 by 10 lakh to 1 by 10,000 millimeter cube. In EDM, geometric of tool, positive impression of hole or geometric features, and tool wear once again depend on the thermal properties of tool material. Local temperature rises is rather high, but there is enough heat diffusion. If very small pulse on time is there, then the hash is limited between 2 to 4 micrometer. Rapid heating and cooling leads to surface hardening, which may be desirable in some of the applications. Tolerance value is between plus minus 0.05 millimeter, which could be easily achieved by EDM. And base surface finish that can be economically achieved on steel is 0.40 micrometer. Now let's have a look for the application. Basically, it is used for drilling of micro holes, thread cutting, helical profile milling, rotary forming, and curved hole drilling. Delicate work piece like copper parts can be produced by EDM. It can be applied to all electrical conductive materials and alloy irrespective of their melting point, hardness, toughness, or brittleness. Other application deep small die holing using tungsten wire as tool, narrow slot, cooling hole in superalloy turbine blade, and various intricate shape can also be performed. EDM can be economically employed for extremely hardened workpiece. Since there is no mechanical stress present, fatigue and slender workpiece place can be machined without distortion. Hard and corrosion resistant surfaces essentially need for die making can also be developed. As well as uses of tubular tool electrode where the dielectric is also flushed. When solid rod are used, dielectric is fed to the machining zone by either suction or injection through pre-drilled holes. Irregular, tapered, curved as well as inclined holes can also be produced by EDM. Creating cool channel in turbine blades made of hard alloy is typically application of EDM drilling. And the next important thing is that NC system enable large number of holes to be accurately located, and it can be performed several times. Now the process has got some application, that is the end sawing. You can see an EDM variation that employs either a special steel band or disc and the cut as a rate that is twice that in conventional and abrasive sawing method. Cutting of billets and bar has a smaller curve and free from burrs, and you can get a surface finish of 6.3 to 10 micrometer with a recast layer of 0.025 to 0.130 millimeter. Now these are the machining of shaper. You can see these are also one of the application. Machining dies and mold. You can see how it is prepared. This is the electrode. This is the electrode. This is the tool path. So in this way it is generated. It is very useful for making EDM. Very versatile, like machining, mechanical milling process. So EDM milling enhanced dielectric flushing due to high speed electrode rotation. Electrode wear can be optimized. Main limitation in EDM is to generate the complex shape with the sharp corner cannot be machined because of the rotation of the electrode. Now the application of wire EDM. As you can see, the special form of EDM we'll be discussing later in my next lecture, where we are going to talk about only the WEDM. And the application is machining of super hard material like polycrystalline diamond, cubic boron nitride, and other composite also. So we'll be discussing about the application of WEDM in my next lecture, where we are going to discuss elaborately about the WEDM. So this is the application of WEDM. You can see this is the wire. This is the dielectric fluid that is ejected. Dielectric supply is occurring here. Where is there? This is a CNC movement. Application of EDM insulator. As you can see, a sheet metal mesh is placed over the ceramic material. This is the ceramic material and this is the mesh metal. This is the dielectric, this is the electrode. If I talk about the application texturing, it has got a final stage of cold rolling, short blasting, but limitation is that it includes lack of control and constituency of texturing, and that need for protection of other parts too. So texturing is achieved by producing electric spark across the gap between the roll and the tool electrode in the presence of some dielectric, that is basically preferred as paraffin. So just we are going to have a look on the advantages. Obviously EDM has got several advantages, we cannot ignore it. Some complex shape that could be difficult for any conventional machine tool, it can be done through EDM. Extremely hard material is preferred here to get a very close tolerance. Very small workpiece where conventional cutting cannot be there or it can damage the part, it can be done here. And there is no direct contact between the tool and the workpiece, therefore delect section and the wick material can be machined without any distortion. Of course, a good surface finish product can be obtained here. But it has got some disadvantages. Every process has got some advantages and disadvantages too. Similar, it has also got. And that is the slow rate of material removal. Economic production, the surface finish specified should not be too fine. Additional timing and cost also it is little bit for ram or sinker EDM. And reproducing sharp corner on the workpiece is very difficult due to electrode wear. Specific power consumption is also very high. Power consumption is too high, overcut is formed. Excessive tool wear occurs during machining, and basically electrically non-conductive material can be machined only with a specific setup process. So thank you, and the thing that we have studied here is basically all about the EDM. So in my next lecture I am going to talk about in a details about the CNC wire cut EDM. So please stay connected and follow up my video. If you have liked the video, please subscribe the channel and like the video too. Thank you.